Penicillins all have a similar structure consisting of a thiazolidine ring connected to a four-membered beta-lactam ring. Antibiotics that contain this beta-lactam ring are sometimes referred to collectively as the beta-lactams. This is what the structure looks like. You'll notice that there is an R group coming off the beta-lactam ring. This is where structural modifications are made to create the different classes of penicillins. But how do penicillins work, and how do they kill bacteria? Penicillins inhibit the growth of bacteria by interfering with the transpeptidation reaction. This in turn inhibits bacterial cell wall synthesis. Getting a bit more detailed, the enzyme penicillin binding protein, commonly abbreviated as PBP, also known as transpeptidase, is essential in the formation of the crosslinks that make up the bacterial cell wall. Shown here are their peptidoglycan polymer chains with attached amino acids. Inhibiting penicillin binding protein, or transpeptidase, inhibits peptidoglycan cell wall crosslinking, leading to a lack of cell wall rigidity and bacterial cell death. It is important to note that penicillins only kill bacterial cells when they are actively growing. Beta-lactamases are a big deal to penicillins because beta-lactamases break the beta-lactam ring, which renders the penicillin inactive. Shown here again is the base structure of penicillin, and beta-lactamases act right at the bottom of the beta-lactam ring, breaking the bond between the carbon and nitrogen and opening up the ring. This structural change to penicillin is what renders it inactive by preventing penicillin interaction with transpeptidase or penicillin binding protein. In addition to beta-lactamases, other mechanisms of bacterial resistance to penicillins exist, and these include altering the porins, altering the molecular structure of penicillin binding protein / transpeptidase, and the upregulation of penicillin efflux pumps. Porins are the gateway for penicillins to access the cell wall in a gram-negative bacterium. You'll recall that gram-negative bacteria have an outer membrane that surrounds the peptidoglycan cell wall. In order for penicillins to penetrate a gram-negative bacterium, they must pass through porins located in the outer membrane. Some gram-negative bacteria are able to develop a resistance to penicillins by altering their porin channels, and thus preventing penicillins from entering the cell to inhibit cell wall synthesis. The structure of penicillin binding protein, or transpeptidase, is also an important factor in penicillins eliciting an effective inhibition of cell wall synthesis. Some bacteria are able to generate resistance to penicillins by altering penicillin binding to the penicillin binding protein, i.e. transpeptidase. This usually occurs due to point mutations that occur in the penicillin binding pocket. If penicillin is unable to bind to penicillin binding protein, or transpeptidase, then penicillin is unable to inhibit the cell wall synthesis. The final method of resistance to penicillins is due to increased efflux of the penicillin itself. Some bacteria are able to upregulate efflux pumps that actively transport penicillins out of the cell after it has entered. Normally, penicillin is able to kill the bacteria. However, efflux of penicillins decreases the intracellular concentration of the penicillin and decreases their effectiveness to inhibit cell wall synthesis. This leads to bacterial survival. In the videos that follow, we will be looking closer at specific penicillin drug classes, including penicillin G, aminopenicillins, penicillinase or beta-lactamase resistant penicillins, and anti-pseudomonal penicillins. This concludes the video. Thanks for watching. Please direct any questions to me on Twitter at Sheehy_Ryan. I've also included my sources here. Thanks again.